Hello again. Welcome to our second lecture video for thermodynamics. Today, we will tackle dimension, units, and dimensional homogeneity. Fundamental concepts are difficult to describe without establishing descriptive names to basic definitions. If we need to know what is mass, and if a mass is defined as that which has inertia, then what is inertia? So, in a dimensional system presented here, these descriptive names are called dimensions. In other words, a dimension is the type of physical quantity. And dimensions are grouped into two categories, fundamental and derived. I will state the entities belong to these categories later. While the unit is a means of assigning a numerical value to that quantity. And you should take note that SI units are preferred in this scientific work compared to other system of units. Now, let us talk about the two categories of dimensions. First, we will tackle about the fundamental or primary dimensions together with their SI units. So, these are the entities. For the fundamental units, we have the mass, right? This one. We have the mass, and the SI unit is in kilogram, and the length, and the SI unit for length is in meter, and the time with symbol T has SI unit of seconds. And for the temperature, the SI unit for temperature is in Kelvin. As for the derived or secondary dimension, it can be expressed or derived from fundamental dimensions. Say for instance, this force. So it is derived from mass times acceleration, where mass is a fundamental dimension, and the acceleration is derived from length over time squared. And length and time are both fundamental dimension. And the SI unit for the force is the Newton, is 1 Newton, or this is equivalent to kilogram meter per second squared. The next example is the pressure. Pressure is given by force per unit area. And we have showed earlier that force is a derived quantity derived from mass and acceleration, while the area is derived from length times width. And length times width are both fundamental dimension. And the SI unit for pressure is Pascal. For the energy, and since energy has many forms, say for instance, we have the potential energy given by mass times gravity times the height. So mass is a fundamental quantity. G is an acceleration, which is derived from length and time. And the height is a fundamental dimension through length. Another example is the kinetic energy. So kinetic energy is given by 1/2 mv squared. And velocity is derived from distance over time. Distance is a type of length. And another form of energy is the elastic potential energy. And this is given by 1/2 kx squared. So k is a constant and x is type of length. So the SI unit of energy is joule, or this is equivalent to Newton meter or kilogram times meter squared per second squared. And the last example is the density. And this is derived from mass over volume. And volume is given by length times width times height. And this width and height is a type of length or distance, okay? And the SI unit for density is kilogram per cubic meter. Kilogram per cubic meter. Okay. Next, this is the standard prefix in SI units. So, it is used to express the multiples of the various units. And you need to familiarize this prefix to simplify your units. So, the typical prefix that are often used in problems is this one, the kilo, and the milli, the micro, the nano, and the pico. So we can write this one as for the kilo. For the kilo, we can write this one as 1 times 10 cubed, or this is equivalent to 1, and this is the decimal point, and you count 3. 1, 2, 3. Put 0 this one. So this is equivalent to 1,000. So 1 kilo is 1,000. This is 1 kilo. So for the centi, this is 1 times 10 to the negative 2. And this is equal to 1. So we have the decimal point here. And since the superscript is negative 2, we move the decimal point to the left. 1, 2. We put 0, and the decimal is moved here. So 1 DC is equivalent to 0.01. For the milli, this is equivalent to 1 times 10 to the negative 3. And this is equal to 1 with a decimal point here. And you count 3 places to the left. 1, 2, 3. 1, 2. So 1 milli is equivalent to 0.001. And you should let's try micro. 1 times 10 to the negative 6, and this is equal to 1 with the decimal here, and you count 6 places to the left since this is negative. So 1, 2, 3, 4, 5, 6. So 0, 0, 0, 0, 0. So 1 micro is equivalent to 0.12345 6. And this is the way that you can write the scientific notation. And you need to familiarize this one. Okay? Next. Since we are handling equations in this course, an important note to remember is that all equations must be dimensionally homogeneous. This means that every term in an equation must have the same units. And the things that you should consider is that in any equation, each additive term must have the same dimensions. So each additive term, so meaning if L is equivalent to 2 plus 3, if you have an equation like this, so these constants 2 and 3 should have units, right? So you can have, since each additive term must have the same dimension, so meaning 2 can be, say for example, we use the unit as kilogram. So 2 should have 2 kilograms plus 3 kilograms. in order for your equation to be valid. Okay? So they should have the same dimensions. And another is that when adding or subtracting values, the units of each value must be similar to be valid. So just like um, this example, again, your values should have the same equations, um, dimensions, I mean. So for the third consideration, a dimensionally homogeneous equation is an equation which has balanced units on each side. For example, the very simple equation, force, this one, force is equivalent to mass times acceleration. The SI unit for force is Newton, and Newton, SI unit for mass is kilogram, and the SI unit for acceleration is meter per second squared. This means that 1 Newton is equivalent to 1 kilogram meter per second squared. Okay? So, this is not equal or this is not valid if your Newton here is grams per meter per second squared. If this is the given, you should convert this to kilograms in order for your equation to be valid. Okay? So let us now check your understanding. Let's identify below if this is a dimensional homogeneous or not. So, example, number 1. Wait, for number 1, F F is equal to mass times acceleration. And the given for mass is in kilogram, and your acceleration is meter squared per second. Since force is in Newton, and your mass here is kilogram meter squared second, and we have learned from the previous slide that 1 Newton is equivalent to 1 kilogram meter per second squared. Meaning for number 1, this one, this is not a dimensional homogeneous. Okay, this is not because Newton is not equal to kilogram meter squared per second. For number 2, um, raw density, raw is equivalent to mass over volume. So mass is in kilogram. This is the SI unit for mass. And the volume is cubic meter. Okay, now, since the given is mass over cubic centimeter, again, this is not a dimensional homogeneous. Not a dimensional homogeneous because of these reasons. Mass is not in kilogram, and the SI unit for volume is cubic meter. So we need to convert this one, convert to cubic meter. Okay. Next. Next is for number 3. This is given. L is equal to is in meters. So the equation in the right hand side is 2xs plus 3. The question is, what should be the unit for the constants 2 and 3 to make it a dimensional homogeneous? So x here is the unknown. So since this is in seconds, so to cancel the second here, x should be in meter per second to cancel the seconds. Okay? And plus 3, since the left-hand side is in meter, and again, for you to achieve a dimensional homogeneous equation, the left-hand side and the right-hand side should be equal or similar in units. So since this is in meter, so 3 should be in meter. So 2 meters plus 3 meters, this is equivalent to 5 meters. So your length is equivalent to 5 meters. And 5 divided by 1,000 is equivalent to 0.005 kilograms. So solving for F, um, F is equivalent here. F is equivalent to mass times acceleration, and mass now is equivalent to 0.005 kilograms. And acceleration is 9.81 meter per second squared. So F is equivalent to 0.005 kilograms times 9.81 meter per second squared. So by using the calculator, 0.005 times 9.81 equivalent to force is 0.04905 kilogram meter per second squared, or approximately equal to 0.05 Newton, since kilogram meter per second squared is equivalent to Newton. Okay, that is for example number 1. Solving for the kinetic energy. Kinetic energy is equivalent to 1/2 mv squared, and mass here is 10 kilograms raised. Mass here is 10 kilograms, and the velocity is 5 centimeter per second. And the mass is already in SI unit, which is in kilogram, and the velocity is in centimeter per second. So meaning we need to convert the velocity 5 centimeter per second to meter per seconds. So now 1 meter is equivalent to 100 cm. Okay? Convert this one 5 centimeter per second. To cancel the centimeter here, we need to put the 100 centimeter at the denominator, and the 1 meter is in numerator. Okay? So cancel, and retain the seconds. So this is equivalent to 5 meter over 100 seconds. And using the calculator, 5 over 100 is 0.05 meter per second. Okay? So our velocity is now converted to SI units. So solving for the kinetic energy, you need to erase this one. Okay. Solving for kinetic energy, here, kinetic energy is V squared, 1/2 mv squared. Okay. So kinetic energy is equivalent to 1/2 times 10 kilograms times our velocity is 0.05 meter per second squared. Okay, using the calculator, 0.5 times 10 times the square of 0.05. This is equal to 0.0125. Kinetic energy is 0.0125, and the unit for SI unit for energy is joule, or this is equal to 0.0125 kilogram meter squared per second squared. Okay, so I think that's the end of our lecture, and for the next lecture, we will tackle about the basic concepts of thermodynamics, and this includes system, state postulate, equilibrium, process, and cycle. And another is the temperature, pressure, and the gauge pressure. Okay, so I will see you next meeting, and ciao.